Chapter 12, Section 2, Congruent Polygons. Continuing on with our congruent triangles unit, there's a reason why they kind of backtrack a little bit here to the name polygons. So for the record, a triangle is a type of polygon. Just to clarify what polygon means, it just means a many-sided figure, many sides. So this is more generalized than the unit name about congruent triangles. So what this is basically saying is it's backing off a little bit into like, all right, well, what happens if any shape is congruent to another shape? And this, we're not going to get too deep into this. We're just basically going to introduce this concept right here, a congruence statement. And this is an overarching theme when we're talking about two objects being congruent. And there's a reason why we stick with triangles here early on in the math career when we deal with proving congruence. And that's because there are limited things that can be congruent to each other. So in one of the simplest figures, one of the simplest two-dimensional figures to draw, a triangle, this is all the information that can be gathered by saying that two triangles are congruent. So for instance, in this example, if triangle XYZ is congruent to triangle MNP, these are all the corresponding pieces that must be congruent to each other. Because ultimately, that's what this is stating. That if I have two objects, triangles in this case, if I have two objects that are congruent to each other, every corresponding piece, and here's that word corresponding. We've seen that in previous chapters. Corresponding basically means same position, same circumstance. Okay, so for instance, angle X, if I were to flip these around, twist them in whichever way so that they were to like be right on top of each other, like completely eclipsing each other, angle X right here would match up with angle M. Angle Y would match up with angle N. Angle Z with angle P. That's what these are saying right here, because these are what we would call corresponding pieces. Even though this is not oriented the same way as this triangle, if I were to move it around and from our previous chapter do a series of transformations mapping this guy onto that guy, these would be the pieces that would match up. And here are the corresponding sides. So X to Y would be the same thing as M to N. Y to Z would be the same thing as N to P. And then Z back to X would be the same exact thing as P back to M. Okay, so this is what we would call a congruence statement, that within two triangles, these are all the pieces of information that are true. And obviously with a more complex pair of figures, had these been quadrilaterals, four-sided figures, or had they been like pentagons or decagons, the more complex the shapes, the more information that has to be shown is congruent. Part of the purpose of this unit is saying like, all right, well, if this is all the information that I can gather from the two pieces being congruent to each other, what's the minimum information that I can show that leads to all the other pieces having to be congruent? That's pretty much what the future sections will start exploring. But for right now, this is what a congruent statement is. Within this object, here are all the matching pieces to this other object that it's congruent to. Okay, so we're going to be doing two examples. And just to clarify again on this, these are two-dimensional objects, and simple two-dimensional objects at that, being triangles. Could you imagine how difficult it would be to, like, say, list out all the dimensions of just this pencil? And you may think, well, shoot, that sounds easy. Just measure the length of it. Well, no, it's not quite that easy. If I have another pencil that's congruent to this, the exact same as this, everything from the circumference here at the tip of the pencil along this ridge growing up to here where it was sharpened, to noticing the angles and the flat sides to this pencil, everything from the white stripe here to the blue stripes to the size of the lettering. When two objects are congruent, every last measurable element is going to match the other. And the more complex an object, even this pencil, is entirely complex. So if I can say that this pencil is congruent to another of the same make, I know I can count on this being all the same measurable quantities. A very valuable thing to do. So in our two examples, I'm going to be doing this on a whiteboard in just a moment. we're basically given this. You'll either start one of two ways. Either one, you will start with these two figures are congruent to each other. Now, based on congruent statements, you're going to be able to match things together and solve for variables or match pieces to its corresponding piece. Or it will start telling you pieces of information about the two figures, and you have to determine if they're congruent. Basically, you're looking for anything being violated in this. Are all the angles, are all the corresponding angles matching? Are all the corresponding side lengths matching? That's what we're looking for congruence. So let's jump to our whiteboard and we'll do these two examples for section 2. And again, the congruence part, we will be talking about how to shortcut these ways in future sections, so we don't have to go through all the information in order to achieve our goal. So here in our first example, we're given two quadrilaterals, DEFG and SPQR. Forgive my kind of sloppy drawing in this one. Normally I'm better about that. But I have two quadrilaterals, obviously kind of twisted around. They don't exactly match side by side. I would have to take this guy and rotate it around before it kind of matched it. That goes back to chapter 11 with how using transformations I could move this guy to make it look like this guy and map it onto that. Basically like a child's toy where I have a block right here. I'm trying to get into this hole. I need to move it around, transform it a few ways before I can line it up. That's basically what chapter 11 was about. But in this, I don't need to twist it around. I'm told right off the bat that these two figures are congruent. Now here is a hint. Pay attention to this. They give you a massive hint at the beginning what should match with which. And it's how this is written. Basically, they go in order. D came first, S came first. Those two angles need to correspond. So this D, 102 degrees, has to be the exact same angle as angle S. It doesn't ask me anything about angle S here, but that will have to match with that. And the second letter, E, will correspond with P, F with Q, G with R. That's a massive hint that is given in every one of these problems. If you're told the two figures, however complex, whether it's a triangle or quadrilateral or something way more complex than that, if you're told the two figures are congruent, it actually will break down in order what pieces will correspond with which means segment DE has to match SP, EF matches PQ, FG, QR, so on and so forth. Okay. All right, so before I jump into this example, another thing to just quickly break down, get used to reading these kinds of diagrams. There's a lot of information on here, and we have to distinguish between what's what, because we technically have two different things that are being measured here. Angles, and you're going to see these little degree symbols. They'll typically be wedged into where the angle is located or pointing into that wedge. Something like this can be tricky for someone. Again, there's that little degree symbol referring to like that's what this angle is. When you don't see a degree measurement, and typically you'll see it kind of hovering above where a segment is or below where a segment is, these refer to side lengths, that 8, 12, and 2x minus 8. So again, just get used to that. The big tell is that for angle measurement, you're going to see degrees. For side length, you're not. Okay. All right. So in this problem, we're asked to solve for each variable. For the record, here in this drawing, they give us more information than we actually need. So we're just going to try and match up the pieces that will correspond, and then we're going to use that to solve for variables. Now, some of you may be tempted to start with this guy. The reason I wouldn't is because there are two variables hidden in there, and I want to solve for one of them before I try plugging into that guy. That's too much to solve for in one go. So I'm going to start here. I want to figure out what this 2x minus 8 matches to. So in some cases, like in this drawing, it's easy enough to say that, okay, well, this side right here is the same thing as this side up here. And I can see that this side length, DE, is 8, and this SP is 2x minus 8. Well, those have to match. They have to be congruent. And we'll write an equation about that in a second. In other cases, maybe it's not as obvious which piece goes where. But again, I could refer back up to here. S to P is going to match the first two letters in this guy, D to E. So I could tell me which segment piece I'm going to match it with. Okay, just as a little hint. But more simply put, here's the equation I'm going to get, that this SP distance has to match this DE distance. And the way I would write that mathematically, if they match or are congruent, is I would say 2x minus 8 has to equal 8. That 2x minus 8 has to be congruent or equal to that 8 length. So that's mathematically how it would be written, and now it just becomes a chapter 1 problem. Solve for your variable. Add 8 to both sides. I get 2x equals 16. Divide by 2, and x equals 8. Done solving for x. And now that was useful to do first because now I can use that for this one that has 2 variables hidden away in it. But now again, I need to set myself up an equation. What matches or has to be congruent or equal to angle Q? If I need to refer up here, Q is the third letter. It has to match angle F. Or maybe even just visually, you can see like, oh, that little kind of longer pointy piece has to match this longer pointy piece right here. And I can see that 6y plus x has to match or equal 68 degrees. And so my new formula is now 6y plus x equals 68. And you can put the degree signs in both cases. All right, but we do have a little bit of help here because we just solved for x. This is the same x as here, so that's 8. So now I have 6y plus 8 equals 68. And again, chapter 1 problem. Subtract 8 from both sides, and I get 6y equals 60. And now divide by the 6. Y equals 10. There's our other variable. Had I started with this guy, I would have gotten y equals and then some version of x on the other side, and I'd have to go back and do this guy first, one way or the other. All right, so there's that example. Let's move on to our second and last example from section 2. All right, in this case, we're given another diagram, pretty complex overlapping set of triangles. I have this bigger triangle, BDC, that's kind of overlapping a little bit with ACD over here on the left. And we're told to find the measurement of angle BDC. So it always helps to be able to map this out first and go in order. BDC. BDC. And you may be tempted to say, oh, it's 30 degrees. But just to clarify, that 30 degrees is wedged just inside in there. We're looking for this whole angle. Okay? And we're going to use a couple of tricks up our sleeve to get to this guy. First, the information they've given us is done on purpose. That 45 degrees wedged in there, they tell us that's 45 for a reason. The 30 degrees wedged in here, they tell us that one for a reason as well. And we see these arches. Okay? These arches refer to matching angles, congruent angles. Single arch matches with single arch. So this angle B also has to be 45 degrees. That's useful. And you'll see why in a minute. This little wedge angle right in here, the 30 degrees that's pointing to, that also means that that double arch matches this guy. So this must be 30 degrees as well, because that's what those arches mean. Why did we go through that process? Because now let's again focus on BDC. B to D to C is this angle here, that whole angle that's being kind of split by the other triangle overlapped, right? Well, and here's where we're going to use the other theorem that we kind of brushed over a little bit in section 1, but it's called the triangle sum theorem. In any triangle, and there are several that are drawn in here, but we're going to focus just on BDC, this longer triangle here on the right. In this triangle, all the internal angles have to add to 180 degrees. And so if I'm focusing just on BDC, this guy right here, each of the 3 angles have to add to 180. Well, now I know 2 of them, 45 and 30. So it can help to maybe do this. I can kind of separate this out. There's BDC. Okay. We know this guy's 45. We know this guy's 30. I can use that information to find angle D here. Now, obviously, this is a far more simplified version of this, but it's still the same end goal, BDC. And so ultimately, here's the math formula we're going to put together. And many of you would be able to do this kind of in your head, but I would have 45 degrees plus the 30 degrees. There's 2 of my angles inside that triangle, plus some unknown. We call that unknown x. And because of triangle sum theorem, those 3 angles have to add to 180 degrees. 45 plus 30 is 75 degrees. Still plus my unknown is 180. And here's the part where many of you would have done this in your head. Add the two together, subtract from 180. Here's why that happens algebraically, but I subtract from 180 and I get x, or angle BDC is 105 degrees.